In a previous lab, we made the assumption that a hot piece of metal was our system and that the water was all of the surroundings that mattered. We know, however, that the heat that was radiated off by the metal also went into the styrofoam cup, the air, and the thermometer, as well as, to a lesser degree, other parts of the room. We ignored these parts and just said that the system and the surroundings had equal and opposite energies, or heats, and so negative Q of the metal was equal to Q of the water. This week we are going to try to take into account the other part of the surroundings that we can measure, the calorimeter. The calorimeter will include the styrofoam cups, the thermometer, the air, and the lid. Let's suppose that we start with 98.2 grams of cold water and that it has a temperature of 20.1 degrees Celsius. Our hot water is 99.1 grams and we have a temperature of 71.2 degrees Celsius. We mix the two together in our coffee cup calorimeter and the final temperature is 41.5 degrees Celsius. So we are expecting that the heat given off by the hot water should be the same as the heat that was absorbed by the cold water. Let's see if this is a valid assumption. We're going to use Q is equal to mc delta T for both sides of this equation. For the hot water, we'll plug in the 99.1 grams and the change in temperature as 41.5 minus 71.2. Remember that it is final minus initial, and so this, for the hot water cooling down, will give us a negative heat. Now we should only have 3 sig figs in our answer, but our number has more digits than that. When we have a large number that needs to be rounded to very few significant figures, what we can do is change the digits that are not significant to 0. To find the heat that is absorbed by the cold water, we are going to do 98.2 times 4.184, the specific heat capacity of water, times the change in temperature, which is 41.5 minus 20.1 degrees Celsius. Remember again that the final temperature needs to come before the initial temperature. This will give us a positive value for Q, which is appropriate because the cold water is absorbing heat. Notice again that we only have 3 significant figures, and so we have changed the last digit to 0 and we have not written a decimal point. So, did we find that the Q, or heat, of the hot water was the same as the Q of the heat of the cold water? We did not. The difference here is that all of the additional heat that should have gone into the cold water went elsewhere, mostly into places like the styrofoam cup, the thermometer, and the air around the styrofoam cup. Let's suppose we mix together 103.65 grams of hydrochloric acid and 109.79 grams of sodium hydroxide. When we do this, the temperature changes from 21.1 to 42.5 for a temperature difference of 21.4. Now this is a little confusing because our reactants contain both the chemicals that are the system, the HCl and the NaOH, and the water. So a simple way to think about this is that the mass of the liquids that we added is approximately the mass of the water. So we can use the 213.44 as the mass of the water. We know the heat capacity of water and the temperature change, so we can find out how much heat the water absorbed. So when we plug in the 213.44 grams and the 21.4 degrees Celsius, we get 19,100 joules. We only have 3 significant figures due to the temperature, so we've changed the last 2 digits to 0. So is this heat the Q of the surroundings? Are we ready to set it equal to the Q of the reaction? Remember that our surroundings, in addition to the water, also include the calorimeter, and we're going to take that into account. Let's see how that works. We're going to assume that the calorimeter has the same temperature both initially and finally that the water does. And so the temperature change will be the same. Let's say that in the first part of this lab, we determined the heat capacity for the calorimeter to be 65 joules per degree Celsius. This means for every one of those 21 degrees that the temperature changed, the calorimeter absorbed 65 joules. So we need to know the total amount of energy absorbed by the calorimeter. Remember that the calorimeter is not the same throughout. Part is styrofoam, part is the metal and the plastic of the thermometer, part is the air. So we aren't going to use per gram. We're just going to use the 65 joules per degree Celsius and multiply that by the temperature change for 1400 joules. This is pretty small, but it's not negligible compared to the amount that we have for the Q of the water. Adding together the heat that was absorbed both by the water and the calorimeter, we have 20,500 joules. This is the surroundings. So the system or the reactants are opposite in sign, but same in magnitude. So the Q of the reaction is negative 20,500 joules. Now, is this what we're looking for? Is this the enthalpy of the reaction? We are trying to find the enthalpy in kilojoules per mole. So we want to know how many moles of this reaction happened. So we take the reaction equation as it is written. You can see it at the top of the board here. And as it is written with its lowest possible coefficients and in the balanced equation, this is 1 mole of reaction. But we didn't use 1 mole of HCl or 1 mole of NaOH. So we're going to have to determine how much we actually used. We used 100 milliliters of each of our reactants. So for either one of them, we can take that 100 milliliters and convert it to liters and then multiply by the molarity of the solution. We actually have two significant figures, 3.0 moles per liter. And so this gives us 0.30 moles of either reactant or of either product. So the enthalpy of the reaction is going to be Q divided by N, our negative 20,500 joules, divided by the 0.30 moles. Since we only have two significant figures in our moles, we come up with 68,000 joules or 68 kilojoules per mole. This should be negative because we have an exothermic reaction. Note that most chemical reactions have enthalpy changes in the order of kilojoules per mole, so this is pretty normal.